Hey, welcome to Physics 1403, Stars and Galaxies. What's going to happen to our sun? So our sun is about 4.5 billion years old and has about 10 billion years worth of hydrogen. What's going to happen next? Well, our star is going to become a red giant. It's going to leave the main sequence where it's been for all of its life, from birth until now, and it's going to become a red giant. And when that giant phase happens, it's not going to be good for Earth. Okay, pretty much guarantee that Mercury and Venus are going to get eaten by the expanded sun. All right, and Earth and Mars may or may not be actually in the atmosphere or the corona of the sun, but our habitable zone, that zone where water can exist as a solid, liquid, and a gas, will no longer include Earth. We will be too close, but it may include Jupiter and Saturn. Okay, so what's going on? So what's going on is that our universe, including our sun, is a very dynamic place. We always kind of look up at the night sky and say it's not changing, it's never changing. Yeah, we notice seasonal changes and nightly changes perhaps, but we don't necessarily think of stars undergoing changes. But they do. And in the case of an intermediate mass star, think the mass of our sun. Think about zero point 0.4 solar masses up to maybe 4 solar masses, somewhere in that area, kind of an intermediate range. When it burns through its hydrogen, it's going to undergo a phase change. It's going to become this red giant. So what's happening is at the core of our sun, we are fusing hydrogen right now. But that hydrogen is being replaced with helium, but it's being replaced, 4 hydrogen nuclei are being replaced by a single helium nuclei. And that is going to have an effect. What's more is that helium is beginning, because it is denser than hydrogen, is beginning to pool at the core of our sun. And it is going to eventually, there's not going to be enough hydrogen left in the core for fusion to continue happening. And so when that happens, which is going to be in about 5 billion years from now, our core will no longer have the outward gas pressure, right, to support itself. And it will begin to contract. Now, I may occasionally accidentally say collapse, but I'm going to try very hard to say contract because collapse makes you think, oh, like supernova, very bad. Right? But it is going to contract. And there's going to be two things that are going to stop that contraction. One is degenerate gas pressure. You just can't have two, two atoms or two nuclei occupy the same space at the same time, even in the center of an intermediate mass star. So you have this degenerate gas pressure, which is actually the pressure of the electrons refusing to occupy the same space as each other, or the protons and that sort of thing. There's also something called neutron degenerate neutron pressure that we'll talk about in a future video. So you're going to have this degenerate pressure, and this degenerate pressure does not depend on temperature. All right, so it's not like normal gas pressure. All right, but you are also going to have, as it collapses towards the center, remember, anytime you collapse something, you contract it, particularly if you're contracting it under a lot of gravitational force, right? It's going to heat up. This is the same thing that happened at the birth of the star with the protostar. Remember, started as a big ball of gas, and as it contracted under gravity, it heated up, and when it reached a certain temperature, hydrogen fusion began. Well, the same sort of thing is going to happen here, only instead of hydrogen fusion, because there isn't enough hydrogen fusion to fuse in there, there's no hydrogen. Instead, it's going to reach a temperature of about 100 million Kelvin versus the 15 million Kelvin that it is now. And that's going to be hot enough for helium to begin to fuse together. And that helium, you're going to take, this is sometimes called the triple alpha series. You're going to take 3 helium atoms and you're going to make a carbon atom, all right, or a nuclei. All right, and oftentimes in the process, you're also going to make an oxygen nucleus. And so this is going to be happening But that increased temperature, there's still a lot of hydrogen in this star. It's just not in the core. That hydrogen is out way in like these shells, away from the core. So as the core heats up, you are going to continue to see hydrogen in a shell surrounding that nucleus. All right. Now this is going to create its own little special problem. And that is now that outward gas pressure from the shell, some of it is pushing in, further heating up the core, but a lot of it is pushing out. And since that pressure is closer to the surface of the star, that is going to push the surface of that star and force it to widen. It's going to become much, much bigger. This is why we call this phase the red giant phase. And the reason it's red is that as this area expands, so again, the core is contracting and heating up, the surface is expanding and thus it is cooling. And as it cools, it's going to be giving off more and more of those longer wavelengths of light, particularly the red lights. And so our sun will take on a reddish color as it cools and become a red giant. So this is just kind of, I jokingly refer to it as the midlife crisis of a star, because we are going to be about 10 billion years in. We're no longer going to have hydrogen in the core. That core is going to begin to contract. It's going to heat up. It's going to heat up enough that it restarts fusion in the shell. But more importantly for us is that it starts fusion in the core, but this time fusion of helium. And that helium is going to form the carbon and the oxygen, which, by the way, are the source of the carbon and hydrogen and the carbon and oxygen in our bodies. We are, to quote Crosby, Stills, Nash, and Young, we are stardust. And this is where that dust comes from. Now, there is a phase after this for an intermediate mass star called asymptotic gas branch star, or JBS stars, which is going to be the subject of another video. Until then, keep looking at the night sky, enjoying what you see.